Okay, let's unpack this. When we think of these huge scientific breakthroughs, our minds often jump to, like, a straight line, right? A single flash of genius.
Yeah, the heroic narrative.
Exactly. But the reality, as we always seem to find digging into these sources, is way messier. It's full of missteps, loads of confusion, even some funny turns.
Definitely.
So today we're diving into a perfect example. The incredible kind of winding journey to figure out the strong force, the fundamental glue holding atomic nuclei together.
It's a fantastic story.
And we're drawing our main insights here from the Nobel lecture of David J. Gross, one of the key people who cracked this puzzle.
A primary source, which is great.
Right. And for you, especially if you're maybe a physics student trying to navigate these complex theories, trying to grasp the really deep questions, this deep dive offers a bit of a shortcut.
Yeah, a way to understand one of the most amazing theoretical wins in recent history.
And how it just completely reshaped our view of fundamental physics.
Yeah. And what's really fascinating, I think, is how that neat, victorious history we often get taught kind of hides the intense struggle that actually happens in science. We'll dig into this period of, honestly, profound theoretical confusion. It eventually led to quantum chromodynamics, QCD, and this completely revolutionary idea of asymptotic freedom.
Okay.
It's a story not just about discovery, but really about challenging these super deeply held beliefs. And it has massive implications for particle physics, cosmology, and, well, how we even think about fundamental theories.
So our mission today, distill the key insights from Gross's account, give you those aha moments, and hopefully a thorough but still engaging handle on this massive shift in physics.
Sounds good.
Okay, so let's set the scene. Picture the early 1960s. Experimental particle physics was just booming.
Oh, yeah, accelerators were getting better, new particles popping up constantly.
Every few months, something new. But theoretically, David Gross himself called it a time of theoretical impotence.
A strong term, but probably accurate.
Especially for the strong nuclear force, the one binding protons and neutrons. It just seemed completely beyond reach.
And it's a good question. Why was it so mysterious? Looking back, nature was really hiding its cards well.
How so?
Well, the basic building blocks of hadrons, particles like protons and neutrons that feel the strong force were totally invisible back then.
Right, we call them quarks now.
Exactly. But at the time, you could smash protons together as hard as you liked. No free quarks ever popped out. Ever. And even the color charges, which are kind of the strong force version of electric charge, they were just as hidden. You couldn't see them directly.
It got so bad that, really respected physicists like Freeman Dyson basically said publicly, the correct theory won't be found in the next 100 years.
Imagine hearing that. Talk about a challenge if you're a young grad student just starting out.
Seriously.
And it wasn't just pessimism. Field theory itself, which had been this incredible success for electromagnetism with QED, quantum electrodynamics.
Right, the jewel in the crown.
It was actually in deep disgrace for strong interactions.
Yeah.
The big problem was these infinities.
Ah, the calculation nightmare.
Yeah. When physicists tried to calculate things using perturbation theory, basically, chopping up complex interactions into simpler bits.
A standard approach.
Their equations just kept blowing up, giving infinite answers. And this wasn't seen as just a calculational quirk. It was seen as a fundamental flaw.
So the whole framework was suspect.
Pretty much.
Yeah.
It led to this really strong dogma that field theory just wasn't the right language for the strong force. Even Richard Feynman, a giant, said in '61 he didn't subscribe to the philosophy of renormalization.
So renormalization itself, that mathematical technique that seemed to fix the infinities in QED, was widely seen as just what? A trick, like sweeping the real problems under the rug.
That was definitely a widespread view, not a genuine solution, just a way to sort of hide the infinities without understanding them. And then things got even worse with work coming out of the Soviet Union from Landau and his group.
Landau, okay, big name.
It's huge. In the late 50s, they uncovered what's called the zero-charge problem within QED itself.
Even in QED?
Even in QED. They found that if you looked at the theory at really, really short distances, super high energies, the effective electric charge.
Strength of the force you measure.
Right, which changes depending on the scale because of how the vacuum gets polarized. But it looks like it would just vanish completely, go to zero.
That sounds bad.
It sounds fatal.
Yeah.
They concluded QED was fundamentally logically incomplete. And Landau, crucially, believed this wasn't just about QED. He thought it applied to all field theories.
Oh, wow.
which led him to famously decree that the field theory approach for strong interactions was, quote, dead and must be buried.
Okay, this is where it gets really wild, right? Because that zero charge problem, logically, it should have made people look for theories where the charge didn't vanish, where maybe it got weaker at short distances.
You'd think so. That would be the logical path. But Landau's influence was just so enormous that certainly in the Soviet Union, apparently a whole generation of physicists was basically forbidden from working on field theory for the strong force.
Forbidden. Seriously.
That's the story Gross tells. They were just convinced that an asymptotically free theory one, where interactions get weak at high energies, simply couldn't exist. They stopped looking.
Wow. Talk about dogma.
Exactly. So instead, the main approach, especially in the West, became something different. S-matrix theory and the bootstrap.
Okay, what was that about?
The core idea was, look, the fields themselves, the things interacting locally in space-time, you can't directly measure them, so maybe they're unphysical.
Throw them out.
Kind of. The theory should only describe things you can measure, like the S-matrix elements, basically, the probabilities for particles to scatter off each other and turn into new particles.
Okay.
And the philosophy behind it was this thing called nuclear democracy. The idea was maybe there are no truly fundamental particles. All particles are just bound states of each other.
Like everything is made of everything else.
In a sense, yeah. It was a direct reaction to that zoo of new particles coming out of the accelerators. How could you have a fundamental theory with hundreds of fundamental particles? It seemed impossible.
So it sounds like this whole S-matrix thing was born out of, well, frustration.
Absolutely. Utter frustration. If your best theoretical tools, field theories, kept giving infinities or were declared dead by the leading figures, then maybe the whole idea of a traditional theory based on fields and point-like interactions was just wrong. Maybe you needed something completely different.
An intellectual dead end, almost.
Well, it felt that way to some. So with dynamics looking hopeless, physicists turned their attention to symmetries.
Okay, a different angle.
Yeah.
Yeah.
And there was real progress there. The discovery of approximate SU3 symmetry by Gell-Mann and Niemann was a huge step forward. It grouped hadrons into families, revealing underlying patterns.
Like the eightfold way.
Exactly. And this led Gell-Mann and George Zweig to propose quarks as the building blocks making up these patterns.
But wait, you said quarks were invisible?
They were. And that was the catch. Because you couldn't see them, quarks were still mostly seen as just fictitious things, mathematical tricks to explain the symmetries, but not, real particles.
Ah, right. The famous pheasant meat analogy comes in here, doesn't it?
Yes. Gell-Mann's analogy, he talked about using field theory concepts to abstract useful mathematical relations, like using veal to cook pheasant.
And then you throw the veal away.
Exactly. You throw the field theory away. He said it gave you the freedom to sort of play with these forbidden field theory ideas without actually having to believe the theory was right.
Clever, but maybe a bit dangerous.
Well, it was ingenious for understanding the patterns, but Gross argues it diverted attention from the really critical dynamical questions, like why are quarks stuck inside?
Right.
Because even though experimental evidence was mounting that hadrons really did seem to behave as if they were made of quarks, the fact that you never ever saw a free quark made it incredibly hard for people to accept they were physically real. Many top physicists were still deeply skeptical.
And David Gross himself, he actually did his PhD with Jeff Chu, who was a major proponent of the bootstrap idea.
Right, one of the gurus.
But Gross started feeling this whole approach was becoming kind of a tautology. Like it could describe things, but not really explain why or predict anything fundamentally new.
Yeah, he felt it lacked predictive power. He started wanting something more, powerful, a real dynamical theory.
And then things started to shift.
Experimentally.
Dramatically. The deep inelastic scattering experiments at SLAC, the Stanford Linear Accelerator Center, starting in the late 60s. These were game changers.
What did they do?
They fired really high-energy electrons at protons, and what they saw was amazing. It looked like the electrons were scattering off tiny, hard, point-like things inside the proton.
Wait, like not a fuzzy blob.
Exactly, not a fuzzy blob. As if the proton, when you look at it really closely over very short times, was made of these distinct little bits, and these bits seem to have spin 1/2.
Spin 1/2, like electrons. Or quarks, precisely. This whole phenomenon got called Bjorken scaling. The way the scattering happened seemed to scale in a way that suggested these internal parts were almost free.
Almost free.
Yeah.
But they're inside a proton, bound by the strong force.
That was the paradox. And then further work, using theoretical tools called sum rules. Gross and Callan specifically showed these constituents had spin 12, ruling out other options.
Okay.
And then Gross and Llewellyn-Smith used another sum rule to show these point-like things had a baryon number of 13.
Exactly what you'd expect for quarks.
Exactly. For David Gross, looking back, these results just clinched the matter. Quarks couldn't just be mathematical fictions anymore. They had to be real, physical, point-like things inside the proton.
Okay, so the paradox just got sharper. If quarks are real, point-like things inside hadrons, why do we never ever see them come out?
Right.
And shouldn't the incredibly strong forces binding them together completely mess up their point-like nature?
Yeah.
Shouldn't they look smeared out when you hit them hard?
That was the core of the problem, a really profound dilemma. The SLAC experiments were shouting Bjorken scaling, which implied the scattering probability didn't really depend on the energy you hit them with, as if the quarks were basically free inside.
Almost like they weren't interacting much at high energy.
Exactly.
Yeah.
But fundamental work on quantum field theory, especially using the renormalization group by Callan, Szymanczyk, and Wilson,
Okay.
showed that in any interacting field theory people knew about, scaling should be violated. Interactions should get stronger or weaker depending on the energy scale. The coupling constant isn't really constant.
So field theory predicted scaling should break down.
Yes, but the experiments, as Gross put it, showed scaling was in fine shape. It seemed to be working beautifully.
So this was the puzzle that really grabbed Russ. How on earth do you explain scaling? How could you have quarks that act almost free inside a proton, strongly bound, yet never escape?
It seemed completely impossible based on everything they thought they knew about quantum field theory, especially with Landau's zero-charge result looming over everything.
So by late 1972, Gross, who by now really understood field theory and the renormalization group stuff deeply,
Yeah, he was an expert.
he decides to tackle this head-on. And his plan was, well, pretty bold, maybe even crazy.
What was it?
He set out to prove that local field theory could not explain scaling, that it was fundamentally the wrong framework for the strong force.
Prove it wrong, not fix it.
Prove it wrong. His strategy had two steps. First, show that ultraviolet stability, meaning the effective coupling strength, goes to zero at very short distances. What we now call asymptotic freedom was essential for scaling to happen.
Okay, logical step. Scaling implies weak interactions at short distances.
Right. And then the second crucial step, prove that no asymptotically free field theories actually exist.
Prove a negative, that sounds hard.
And it lined up perfectly with the conventional wisdom. Everyone knew QED did the opposite. Its effective charge gets stronger at short distances.
Right, that screening effect.
So the idea that a theory's coupling could get weaker, especially the strong forces coupling, seemed totally impossible. If he could prove no such theory existed, then field theory was out for strong interactions.
A very ambitious goal.
But then came the calculation. Gross, working with his brilliant grad student, Frank Wilczek.
Wilczek, okay.
They decide to actually calculate the beta function for Yang-Mills theory. What's the beta function again?
It's the thing that tells you how the coupling strength changes with energy scale. Calculating it tells you if the theory is asymptotically free or not.
Got it. And Yang-Mills theory.
That's a specific type of quantum field theory, a non-abelian gauge theory. It's the kind of theory needed if the force carriers themselves, like gluons, carry the charge. Different from QED, where photons are neutral.
Okay, complex stuff.
Very. And independently, another student, H. David Pulitzer, working with Sidney Coleman at Harvard, was doing the exact same calculation.
Two groups at once.
Yep. And Gross emphasizes, today, calculating this beta function is a standard, if tough, homework problem in QFT courses.
Yeah.
But back then, it was incredibly hard.
Why so hard?
They were wrestling with really tricky technical issues, making sure the calculation respected the theory's symmetry, gauge invariance, figuring out how to handle the infinities properly, regularization, even just getting the signs right in incredibly complex algebra, lots of minus signs.
I can imagine. Easy to make a slip.
Very easy. But this is where the story just takes an absolutely stunning turn.
Yeah.
February 1973, after months of intense grinding work.
Yeah.
Both groups, Gross and Wilczek and Pulitzer, they finished the calculation. They found the answer for the Yang-Mills beta function, and it had the opposite sign to QED.
Opposite sign, meaning?
Meaning it was negative, which meant the effective coupling strength decreased at short distances. It went towards zero in the ultraviolet limit.
Wait. They found it. The thing they were trying to prove didn't exist?
Exactly. They discovered asymptotic freedom. The very property they thought was impossible, their calculations showed it was real, at least in these Yang-Mills theories.
Wow. Gross described his reaction as being Like an atheist who has just received a message from a burning bush.
Huh. You can imagine the shock. Their whole worldview, the dogma that all field theories had the zero-charge problem, it just shattered.
So field theory wasn't wrong for the strong force.
Not at all. In fact, this discovery flipped everything. If scaling was observed experimentally and asymptotic freedom was necessary for scaling,
Then the strong force must be described by an asymptotically free gauge theory.
precisely, what a complete turnaround.
Okay, so can we understand this physically? Why does it happen? You mentioned screening in QED.
Right. In QED, the vacuum sort of screens the electric charge. Think of virtual electron-positron pairs popping up around a charge. They align themselves to reduce the charge seen from far away, so the effective charge looks weaker at long distances or stronger as you get closer.
Okay, standard picture.
But in these non-abelian gauge theories, like Yang-Mills, the force carriers, the gluons, in this case, they also carry the charge, color charge.
Unlike photons.
Unlike photons. And these charged gluons have a different effect. They act kind of like tiny magnetic dipoles that, instead of screening the color charge, they anti-screen it.
Anti-screen.
Yeah, they align in a way that effectively amplifies the color field as you move away. So the force gets stronger at large distances. And consequently, it gets weaker at short distances. This gluon anti-screening effect is stronger than the usual screening from quark-antiquark pairs, and it's what makes the theory asymptotically free.
That's counterintuitive, but makes sense. The force carriers themselves change the game.
Exactly. And the math was solid, too. The formula they derived for the beta function, it showed that this asymptotic freedom was pretty robust.
How so?
You could have quite a few types of quarks in the theory, up to 16 flavors, as we call them, before their screening effect would eventually overwhelm the gluon anti-screening and break asymptotic freedom.
So plenty of room for the quarks we know about: up, down, strange, charm, bottom, top.
Plenty of room. It made the theory seem very plausible and flexible.
So, with asymptotic freedom discovered, suddenly everything started clicking into place.
With incredible speed. Gross and Wilczek immediately realized, okay, this property explains Bjorken scaling. That mystery was solved.
Oh.
And they proposed right away that the strong interactions must be described by a color gauge theory, based on Yang-Mills theory with quarks and gluons, what we now call quantum chromodynamics, or QCD.
QCD is born.
Basically, yes. And since the deep inelastic scattering showed the constituents were charged quarks, the force carriers, the gluons, had to be electrically neutral but carry color charge. This fit perfectly with existing evidence for color, which helped solve other puzzles like why certain particle states existed.
And they didn't just explain things. You mentioned predictions.
Huge predictions. They immediately realized that asymptotic freedom wasn't perfect freedom. The coupling goes to zero, only logarithmically slowly at high energy, meaning there should be small, predictable violations of perfect Bjorken scaling. Logarithmic violations.
Yeah.
They could calculate exactly how scaling should break down.
That's massive. Going from we can't calculate anything to making precise, testable predictions from first principles.
It was a revolution in thinking, a total shift from just describing patterns to having a fundamental predictive theory.
But it still leaves that other big question. If quarks and gluons are real, why don't we see them flying free?
Right, the confinement problem. Asymptotic freedom didn't automatically prove confinement, but it strongly suggested how it could work.
How?
Because if the coupling gets weaker at short distances, asymptotic freedom, it must get stronger at large distances.
The flip side of the coin.
Exactly. This behavior at large distances was later called infrared slavery. The idea is the force becomes so strong as you try to pull quarks or gluons apart, it's literally impossible. Infinite energy would be required. They're permanently consigned inside hadrons.
A plausible mechanism, even if the math was still hard.
Very hard. But a huge step towards understanding confinement came soon after from Kenneth Wilson.
Wilson?
Yeah, he proposed putting QCD onto a discrete spacetime grid, a lattice gauge theory.
Okay, like a computational approach.
Exactly. It turns the problem into something you can simulate on a computer. And in this lattice formulation, even with crude approximations, you could clearly see confinement emerging when the coupling was strong.
So it showed confinement was likely a real feature of the theory.
Yes, and it opened the door for the incredibly powerful numerical simulations we have today, which can now calculate hadron masses and properties from QCD with amazing accuracy, like a few %.
So how quickly did the physics community accept this new picture, QCD?
Remarkably fast, especially among theorists. Gross called it a phase transition in how people thought.
From skepticism to belief.
Totally. Before asymptotic freedom, most felt they were light years away from a real theory of hadrons. Afterwards, it seemed almost obvious that QCD had to be the right answer.
Why such a rapid change?
Because it just explained so much. It explained scaling at short distances, it offered this compelling picture for confinement at long distances, and it neatly incorporated all the successful symmetry ideas and phenomenology from the previous decade.
And crucially,
perturbation theory, doing calculations piece by piece, which had been useless before, was now reliable and trustworthy at short distances, thanks to asymptotic freedom. Physicists could finally calculate things about the strong force from first principles.
what about the experimental side? Did the evidence follow quickly?
It was a bit slower, more gradual. Initially, there were even some confusing results. For example, measurements of electron-positron annihilation into hadrons, this quantity called R.
Yeah.
It seemed to be rising more than simple QCD predicted. That caused some temporary worry.
The contradiction.
Turned out, no. It was quickly understood as the threshold for producing new, heavier quarks, charmed quarks opening up, something QCD could easily accommodate.
So the theory was flexible enough.
Exactly. And then over the following years, those predicted logarithmic violations of scaling. They were painstakingly measured in many different experiments looking at how protons and neutrons break up.
Yeah.
And they matched the QCD predictions beautifully. In many cases, the agreement is now better than 1%. Just spectacular confirmation.
So good that experimentalists now talk about seeing quarks and gluons directly.
Well, almost. They point to their detector readouts showing these collimated sprays of particles called jets and say, look, here's a quark jet, here's a gluon jet. They're the unmistakable footprints of those fundamental particles.
It really shifted from belief to sight.
As Gross put it, believing is seeing, seeing is believing. The evidence became so compelling that the physical reality of quarks and gluons and the asymptotic simplicity of their interactions at high energy is now just accepted fact.
So let's bring this home. What does all this mean for you, maybe listening as a physics student, trying to make sense of the fundamental theories driving our universe?
Well, first off, discovering asymptotic freedom wasn't just about getting QCD. It fundamentally changed how we think about quantum field theory itself.
How so?
It showed that fundamental theories don't necessarily have to break down or become infinitely complicated at short distances, like the zero-charge problem suggested. Instead, they can actually become simpler, more elegant, easier to calculate.
That must have boosted confidence in QFT enormously.
Hugely. It showed QFT could be a consistent, powerful framework for describing nature right down to incredibly small scales.
And QCD itself became a new kind of theory.
Yes, connecting this to the bigger picture, QCD stands out as our first example of a theory that's essentially complete, with basically no free parameters you can just adjust.
No adjustable knobs.
Well, you have the quark masses, which actually come from their interaction with the Higgs field in the electroweak theory. But other than that, the theory's structure is fixed. And this amazing thing happens called dimensional transmutation.
Dimensional transmutation.
Yeah, it's a quantum effect where the theory generates its own mass scale purely from its dimensionless coupling constant. So all the masses of hadrons, like the proton, 99% of whose mass comes from the energy of the quarks and gluons inside, not their intrinsic mass.
Right, EMC.
That mass is dynamically generated by the theory itself. It's not put in by hand. In that sense, QCD is, well, almost a perfect theory.
Incredible. And the impact went beyond particle physics.
Oh, absolutely. This understanding revolutionized cosmology because we now understand how matter behaves at extreme temperatures and densities.
Like in the early universe.
Exactly. We can extrapolate back to moments just fractions of a second after the Big Bang, when the universe was hot enough for quarks and gluons to exist freely in a quark-gluon plasma.
A state of matter we can now try to recreate in colliders.
Precisely. And maybe the most exciting implication. Asymptotic freedom gave us the first real hint about the unification of forces.
How?
Because the strong force gets weaker at high energy, while the electroweak forces get slightly stronger. Their strengths start to converge. It suggests that maybe at some incredibly high energy scale, perhaps near the Planck scale where gravity becomes strong, all the forces might actually merge into a single unified interaction.
The grand unification dream.
Asymptotic freedom provided the first quantitative clue that this dream might actually be achievable. It showed us where the next frontier of fundamental physics might lie.
So this whole journey, from that deep confusion and theoretical impotence in the 60s to the triumph of QCD and asymptotic freedom, It's just a powerful story about how science really works, isn't it?
Absolutely. Not neat straight lines, but bold ideas, unexpected results from experiments, and crucially, the courage to question even the most deeply held assumptions.
A testament to how sticking with puzzling data, even when it seems paradoxical, can lead to breakthroughs.
Definitely. Which leads to maybe a final thought for you, our listener, especially if you're diving into physics yourself. What other phenomena out there right now seem impossible or paradoxical? Things like dark matter, dark energy, maybe even aspects of quantum gravity. Could they be waiting for a similar kind of counterintuitive breakthrough?
A discovery that forces us to junk some current assumption we think is bedrock truth.
Exactly. A breakthrough that looks completely impossible from today's perspective, but unlocks a whole new paradigm tomorrow.
Definitely something to mull over. We'll see you next time for another deep dive.